Semiconductor Electronics, Materials, Devices and Simple Circuits. Introduction. Devices in which a controlled flow of electrons can be obtained are the basic building blocks of all electronic circuits. Before the discovery of the transistor in 1948, such devices were mostly vacuumed tubes, also called valves, like the vacuum diode, which has two electrodes, namely anode, often called a plate, and cathode, triode, which has three electrodes, cathode, plate, and grid, tetrode and pentode, respectively with 4 and 5 electrodes. In a vacuum tube, the electrons are supplied by a heated cathode and the controlled flow of these electrons in a vacuum is obtained by varying the voltage between its different electrodes. A vacuum is required in the inter-electrode space, otherwise the moving electrons may lose their energy in collision with the air molecules in their path. In these devices, the electrons can flow only from the cathode to the anode, that is, only in one direction. Therefore, such devices are generally referred to as valves. These vacuum tube devices are bulky, consume high power, operate generally at high voltages, that is similar to 100 volt, and have limited life and low reliability. The seed of the development of modern solid-state semiconductor electronics goes back to 1930s, when it was realized that some solid-state semiconductors and their junctions offer the possibility of controlling the number and the direction of flow of charge carries through them. Simple excitations like light, heat, or small applied voltage can change the number of mobile charges in a semiconductor. The supply and flow of charge carries in the semiconductor devices are within the solid itself. No external heating or large evacuated space is required by the semiconductor devices. They are small in size, consume low power, operate at low voltages, and have a long life and high reliability. Even the cathode ray tubes, that is CRT, used in television and computer monitors, which work on the principle of vacuum tubes, are being replaced by liquid crystal display, that is LCD monitors with supporting solid-state electronics. Much before the full implications of the semiconductor devices were formally understood, a naturally occurring crystal of galena, that is lead sulfide PBS, with a metal point contact attached to it was used as a detector of radio waves. Classification of metals, conductors and semiconductors. 1. On the basis of conductivity. On the basis of the relative values of electrical conductivity, sigma, or resistivity, rho is equal to 1 upon sigma. The solids are broadly classified as: Number 1. Metals. They possess very low resistivity or high conductivity. Rho is similar to 10 raised to minus 2 minus 10 raised to minus 8 ohm meter. Sigma is similar to 10 square minus 10 raised to 8 Simon per meter. Number 2. Semiconductors. They have resistivity or conductivity intermediate to metals and insulators. Rho is similar to 10 raised to minus 5 minus 10 raised to 6 ohm meter. Sigma is similar to 10 raised to 5 minus 10 raised to minus 6 Simon per meter. Number 3. Insulators. They have high resistivity or low conductivity. Rho is similar to 10 raised to 11 minus 10 raised to 19 ohm meter. Sigma is similar to 10 raised to minus 11 minus 10 raised to minus 19 Simon per meter. The values of rho and sigma given above are indicative of magnitude and could well go outside the ranges as well. 1. elemental semiconductors, silicon and germanium. 2. Compound semiconductors. Examples are inorganic, cadmium sulfide, gallium arsenide, cadmium selenide, indium phosphide, etc. Organic, anthracene, doped phthalocyanines, etc. Organic polymers, polypyrrole, polyaniline, polythiophane, etc. Most of the currently available semiconductor devices are based on elemental semiconductors, silicon or germanium, and compound inorganic semiconductors. However, after 1990, a few semiconductor devices using organic semiconductors and semiconducting polymers have been developed, signaling the birth of a futuristic technology of polymer electronics and molecular electronics on the basis of energy bands. According to the Bohr atomic model, in an isolated atom, the energy of any of its electrons is decided by the orbit in which it revolves. But when the atoms come together to form a solid, they are close to each other. So the outer orbits of electrons from neighboring atoms would come very close or could even overlap. This would make the nature of electron motion in a solid very different from that in an isolated atom. Inside the crystal, each electron has a unique position and no two electrons see exactly the same pattern of surrounding charges. Because of this, each electron will have a different energy level. These different energy levels with continuous energy variation form what are called energy bands. The energy band, which includes the energy levels of the valence electrons, is called the valence band. The energy band above the valence band is called the conduction band. With no external energy, all the valence electrons will reside in the valence band. If the lowest level in the conduction band happens to be lower than the highest level of the valence band, the electrons from the valence band can easily move into the conduction band. Normally, the conduction band is empty, but when it overlaps on the valence band, electrons can move freely into it. This is the case with metallic conductors. If there is some gap between the conduction band and the valence band, electrons in the valence band all remain bound and no free electrons are available in the conduction band. This makes the material an insulator. But some of the electrons from the valence band may gain external energy to cross the gap between the conduction band and the valence band. Then these electrons will move into the conduction band. At the same time, they will create vacant energy levels in the valence band where other valence electrons can move. Thus, the process creates the possibility of conduction due to electrons in the conduction band as well as vacancies in the valence band. Let us consider what happens in the case of silicon or germanium crystal containing n atoms. For silicon, the outermost orbit is the third orbit, that is n is equal to 3. While for germanium, it is the fourth orbit, that is n is equal to 4. The number of electrons in the outermost orbit is 4, that is 2s and 2p electrons. Hence, the total number of outer electrons in the crystal is 4n. The maximum possible number of electrons in the outer orbit is 8, that is 2s plus 6p electrons. So, for the 4n valence electrons, there are 8n available energy states. These 8n discrete energy levels can either form a continuous band or they may be grouped in different bands depending upon the distance between the atoms in the crystal. See box on band theory of solids. At the distance between the atoms in the crystal lattices of silicon and germanium, The energy band of these 8 n states is split apart into two which are separated by an energy gap Eg. The lower band, which is completely occupied by the 4n valence electrons at temperature of absolute zero, is the valence band. The other band, consisting of 4n energy states, called the conduction band, is completely empty at absolute zero. The lowest energy level in the conduction band is shown as Ec, and highest energy level in the valence band is shown as Ev. Above Ec and below Ev, there are a large number of closely spaced energy levels as shown in figure. The gap between the top of the valence band and bottom of the conduction band is called the energy band gap, that is energy gap Eg. It may be large, small, or zero depending upon the material. These different situations are depicted in figure and discussed below. Case 1. This refers to a situation as shown in figure. One can have a metal either when the conduction band is partially filled and the balanced band is partially empty, or when the conduction and valence bands overlap. When there are overlaps, electrons from the valence band can easily move into the conduction band. This situation makes a large number of electrons available for electrical conduction. When the valence band is partially empty, electrons from its lower level can move to a higher level, making conduction possible. Therefore, the resistance of such materials is low or the conductivity is high. Case 2. In this case, as shown in figure, a large band gap Eg exists. That is, Eg is greater than 3 electron volt. There are no electrons in the conduction band and therefore no electrical conduction is possible. Note that the energy gap is so large that electrons cannot be excited from the valence band to the conduction band by thermal excitation. This is the case with insulators. Case 3. The situation is shown in figure. Here a finite but small band gap, that is Eg is less than 3 electron volt exists. Because of the small band gap, at room temperature, some electrons from the valence band can acquire enough energy to cross the energy gap and enter the conduction band. These electrons, through small in numbers, can move in the conduction band. Hence, the resistance of semiconductors is not as high as that of the insulators. Intrinsic semiconductor. We shall take the case of germanium and silicon, whose lattice structure is shown in figure. Each atom is surrounded by 4 nearest neighbors. Silicon and germanium have 4 valence electrons. In its crystalline structure, every silicon or germanium atom tends to share one of its 4 valence electrons with each of its 4 nearest neighbor atoms. These shared electron pairs are referred to as forming a covalent bond or simply a valence bond. The 2 shared electrons can be assumed to shuttle back and forth between the associated atoms, holding them together strongly. The figure symmetrically shows the 2-dimensional representation of the silicon or germanium structure shown in figure, which overemphasizes the covalent bond. It shows an idealized picture in which no bonds are broken. Such a situation arises at low temperatures. As the temperature increases, more thermal energy becomes available to these electrons, and some of these electrons may break away, becoming free electrons contributing to conduction. The thermal energy effectively ionizes only a few atoms in the crystalline lattice and creates a vacancy in the bond as shown in figure. The neighborhood from which the free electron with charge -q has come out leaves a vacancy with an effective charge +q. This vacancy with the effective positive electronic charge is called a hole. The hole behaves as an apparent free particle with an effective positive charge. In intrinsic semiconductors, the number of free electrons Ne is equal to the number of holes Nh. That is, Ne is equal to Nh is equal to Ni. Equation 1. Where Ni intrinsic carrier concentration. Semiconductors possess a unique property in which, apart from electrons, the holes also move. Suppose there is a hole at site 1 as shown in figure. The movement of holes can be visualized as shown in figure. An electron from the covalent bond at site 2 may jump to the vacant site 1, that is hole. Thus, after such a jump, the hole is at site 2 and site 1 has now an electron. Therefore, apparently the hole has moved from site 1 to site 2. The electron originally set free is not involved in this process of hole motion. The free electron moves completely independently as a conduction electron and gives rise to an electron current, i.e., under an applied electric field. The motion of a hole is only a convenient way of describing the actual motion of bound electrons whenever there is an empty bond anywhere in the crystal. Under the action of an electric field, these holes move towards negative potential, giving the hole current IH. The total current I is thus the sum of the electron current IE and the hole current IH. I is equal to IE plus IH. Equation 2. Apart from the process of generation of conduction electrons and holes, a simultaneous process of recombination occurs in which the electrons recombine with the holes. At equilibrium, the rate of generation is equal to the rate of recombination of charge carriers. The recombination occurs due to an electron colliding with a hole. An intrinsic semiconductor will behave like an insulator at T is equal to 0 Kelvin as shown in figure. It is the thermal energy at higher temperatures, that is T is greater than 0 Kelvin, which excites some electrons from the valence band to the conduction band. These thermally excited electrons at T is greater than 0 Kelvin partially occupy the conduction band. Therefore, the energy band diagram of an intrinsic semiconductor will be as shown in figure. Here, some electrons are shown in the conduction band. These have come from the valence band, leaving an equal number of holes there. Example 1. Carbon, silicon and germanium have same lattice structure. Why is carbon insulator while silicon and germanium intrinsic semiconductors? Solution. The 4 bonding electrons of carbon, silicon or germanium lie respectively in the second, third and fourth orbit. Hence, energy required to take out an electron from these atoms, that is ionization energy Eg, will be least for Ge. That is, ionization energy Eg will be least for germanium, followed by silicon and highest for carbon. Hence, number of free electrons for conduction in germanium and silicon are significant but negligibly small for C. Extrinsic semiconductor. The conductivity of an intrinsic semiconductor depends on its temperature, but at room temperature, its conductivity is very low. As such, no important electronic devices can be developed using these semiconductors. Hence, there is a necessity of improving their conductivity. This can be done by making use of impurities. When a small amount, say a few parts per million, that is ppm, of a suitable impurity is added to the pure semiconductor, the conductivity of the semiconductor is increased manifold. Such materials are known as extrinsic semiconductors or impurity semiconductors. The deliberate addition of a desirable impurity is called doping, and the impurity atoms are called dopants. Such a material is also called a doped semiconductor. The dopant has to be such that it does not distort the original pure semiconductor lattice. It occupies only a very few of the original semiconductor atom sites in the crystal. A necessary condition to attain this is that the sizes of the dopant and the semiconductor atoms should be nearly the same. There are two types of dopants used in doping the tetravalent silicon or germanium. Number 1, pentavalent, that is valency 5, arsenic, that is As, antimony, that is Sb, phosphorus, that is P, etc. Number 2, trivalent, that is valency 3, indium, that is In, boron, that is B, aluminium, that is Al, etc. Silicon or germanium belongs to the fourth group in the periodic table, and therefore we choose the dopant element from the nearby fifth or third group, expecting and taking care that the size of the dopant atom is nearly the same as that of silicon or germanium. The pentavalent and trivalent dopants in silicon or germanium give two entirely different types of semiconductors as discussed below. Number 1, N-type semiconductor. We dope silicon or germanium with a pentavalent element as shown in figure. When an atom of +5 valency element occupies the position of an atom in the crystal lattice of silicon, 4 of its electrons bond with the 4 silicon neighbors, while the fifth remains very weakly bound to its parent atom. This is because the 4 electrons participating in bonding are seen as part of the effective core of the atom by the fifth electron. As a result, the ionization energy required to set this electron free is very small, and even at room temperature, it will be free to move in the lattice of the semiconductor. For example, the energy required is similar to 0.01 electron volt for germanium and 0.05 electron volt for silicon to separate this electron from its atom. This is in contrast to the energy required to jump the forbidden band, about 0.72 electron volt for germanium and about 1.1 electron volt for silicon at room temperature in the intrinsic semiconductor. Thus, the pentavalent dopant is donating one extra electron for conduction and hence is known as a donor impurity. The number of electrons made available for conduction by dopant atoms depends strongly upon the doping level and is independent of any increase in ambient temperature. On the other hand, the number of free electrons with an equal number of holes generated by silicon atoms increases weakly with temperature. In a doped semiconductor, the total number of conduction electrons Ne is due to the electrons contributed by donors and those generated intrinsically, while the total number of holes Nh is only due to the holes from the intrinsic source, but the rate of recombination of holes would increase due to the increase in the number of electrons. As a result, the number of holes would get reduced further. Thus, with the proper level of doping, the number of conduction electrons can be made much larger than the number of holes. Hence, in an extrinsic semiconductor doped with a pentavalent impurity, electrons become the majority carriers and hold the minority carriers. These semiconductors are therefore known as N-type semiconductors. For N-type semiconductors, Ne much greater than Nh. Equation 3. Number 2. P-type semiconductor. This is obtained when silicon or germanium is doped with a trivalent impurity like aluminium, boron, indium, etc. The dopant has one valence electron less than silicon or germanium, and therefore this atom can form covalent bonds with neighboring 3 silicon atoms but does not have any electron to offer to the 4th silicon atom. So the bond between the 4th neighbor and the trivalent atom has a vacancy or hole as shown in figure. Since the neighboring silicon atom in the lattice wants an electron in place of a hole, an electron in the outer orbit of an atom in the neighborhood may jump to fill this vacancy, leaving a vacancy or hole as its own site. Thus, the hole is available for conduction. The trivalent foreign atom becomes effectively negatively charged when it shares 4th electron with neighboring silicon atom. Therefore, the dopant atom of p-type material can be treated as core of one negative charge along with its associated hole as shown in figure. One acceptor atom gives one hole. These holes are in addition to the intrinsically generated holes, while the source of conduction electrons is only intrinsic generation. Thus, for such a material, the holes are the majority carriers and electrons are minority carriers. Therefore, extrinsic semiconductor doped with trivalent impurity are called p-type semiconductors. For p-type semiconductors, the recombination process will reduce the number Ni of intrinsically generated electrons to Ne. For p-type semiconductors, Nh is much greater than Ne. Equation 4. The crystal maintains an overall charge neutrality as the charge of additional charge carriers is just equal and opposite to that of the ionized cores in the lattice. In extrinsic semiconductors, because of the abundance of majority current carriers, the minority carriers produced thermally have more chance of meeting majority carriers and thus getting destroyed. Hence, the dopant, by adding a large number of current carriers of one type which become the majority carriers, indirectly helps to reduce the intrinsic concentration of minority carriers. The semiconductor's energy band structure is affected by doping. In the case of extrinsic semiconductors, additional energy states due to donor impurities, that is ED, and acceptor impurities, that is EA, also exist. In the energy band diagram of N-type silicon semiconductor, the donor energy level ED is slightly below the bottom EC of the conduction band, and electrons from this level move into the conduction band with very small supply of energy. At room temperature, most of the donor atoms get ionized, but very few, similar to 10⁻⁻12 atoms of silicon, get ionized. So the conduction band will have most electrons coming from the donor impurities as shown in figure. Similarly, for p-type semiconductor, the acceptor energy level EA is slightly above the top EV of the valence band as shown in figure. With very small supply of energy, an electron from the valence band can jump to the level EA and ionize the acceptor negatively. Alternately, we can also say that with very small supply of energy, the hole from level EA sinks down into the valence band. Electrons rise up and holes fall down when they gain external energy. At room temperature, most of the acceptor atoms get ionized, leaving holes in the valence band. Thus, at room temperature, the density of holes in the valence band is predominantly due to impurity in the extrinsic semiconductor. The electron and hole concentration in a semiconductor in thermal equilibrium is given by Ne into Nh is equal to Ni squared. Equation 5. Though the above description is grossly approximate and hypothetical, it helps in understanding the difference between metals, insulators, and semiconductors, that is extrinsic and intrinsic, in a simple manner. The difference in the resistivity of carbon, silicon and germanium depends upon the energy gap between their conduction and valence band. For carbon, silicon and germanium, the energy gaps are 5.4 electron volt, 1.1 electron volt and 0.7 electron volt respectively. Tin also is a group 4 element, but it is a metal because the energy gap in its case is 0 electron volt. Example 2. Suppose a pure silicon crystal has 5 into 10 raised to 28 atoms, meter raised to -3. It is doped by 1 parts per million concentration of pentavalent arsenic. Calculate the number of electrons and holes. Given that Ni is equal to 1.5 into 10 raised to 16 meter raised to -3. Solution. Thermally generated electrons Ni is similar to 10 raised to 16 meter raised to -3 are negligibly small as compared to those produced by doping. Therefore, Ne is approximately equal to Nd. Since Ne into Nh is equal to Ni square, the number of holes Nh is equal to Ni square upon Ne. Therefore, Nh is equal to 2.25 into 10 raised to 32 upon 5 into 10 raised to 22 is similar to 4.5 into 10 raised to 9 meter raised to -3. PN junction. A PN junction is the basic building block of many semiconductor devices like diodes, transistor, etc. A clear understanding of the junction behavior is important to analyze the working of other semiconductor devices. We will now try to understand how a junction is formed and how the junction behaves under the influence of external applied voltage, also called bias. PN junction formation. Consider a thin p-type silicon, that is PSI semiconductor wafer. By adding precisely a small quantity of pentavalent impurity, part of the p-type silicon wafer can be converted into n-type silicon. There are several processes by which a semiconductor can be formed. The wafer now contains p region and n region and a metallurgical junction between p and n region. Two important processes occur during the formation of a PN junction. Number 1, diffusion, and number 2, drift. An n-type semiconductor, the concentration of electrons, that is number of electrons per unit volume, is more compared to the concentration of holes. Similarly, in a p-type semiconductor, the concentration of holes is more than the concentration of electrons. During the formation of PN junction and due to the concentration gradient across p and n sides, holes diffuse from p side to n side, that is p to n, and electrons diffuse from n side to p side, that is n to p. This motion of charge carries gives rise to diffusion current across the junction. When an electron diffuses from n to p, it leaves behind an ionized donor on n side. This ionized donor, that is positive charge, is immobile as it is bonded to the surrounding atoms. As the electrons continue to diffuse from n to p, a layer of positive charge or positive space charge region on n side of the junction is developed. Similarly, when a hole diffuses from p to n due to the concentration gradient, it leaves behind an ionized acceptor, that is negative charge, which is immobile. As the holes continue to diffuse, a layer of negative charge or negative space charge region on the p side of the junction is developed. This space charge region on either side of the junction together is known as depletion region, as the electrons and holes taking part in the initial movement across the junction depleted the region of its free charges. The thickness of depletion region is of the order of 1/10 of micrometer. Due to the positive space charge region on n side of the junction and negative space charge region on p side of the junction, an electric field directed from positive charge towards negative charge develops. Due to this field, an electron on p side of the junction moves to n side and a hole on n side of the junction moves to p side. The motion of charge carriers due to the electric field is called drift. Thus, a drift current which is opposite in direction to the diffusion current starts. Initially, diffusion current is large and drift current is small. As the diffusion process continues, the space charge regions on either side of the junction extend, thus increasing the electric field strength and hence drift current. This process continues until the diffusion current equals the drift current. Thus, a p-n junction is formed. In a p-n junction under equilibrium, there is no net current. The loss of electrons from the n region and the gain of electron by the p region causes a difference of potential across the junction of the two regions. The polarity of this potential is such as to oppose further flow of carriers so that a conduction of equilibrium exists. Figure shows the p-n junction at equilibrium and the potential across the junction. The n material has lost electrons and p material has acquired electrons. The n material is thus positive relative to the p material. Since this potential tends to prevent the movement of electron from the n region into the p region, it is often called a barrier potential. Example 3. Can we take one slab of p-type semiconductor and physically join it to another n-type semiconductor to get p-n junction? Solution: no. Any slab, howsoever flat, will have roughness much larger than the interatomic crystal spacing is similar to 2 to 3, and hence continuous contact at the atomic level will not be possible. The junction will behave as a discontinuity for the flowing charge carriers. Semiconductor diode. A semiconductor diode is basically a p-n junction with metallic contacts provided at the ends for the application of an external voltage. It is a two-terminal device. A p-n junction diode is symbolically represented as shown in figure. The direction of arrow indicates the conventional direction of current. When the diode is under forward bias, the equilibrium barrier potential can be altered by applying an external voltage V across the diode. The situation of p-n junction diode under equilibrium without bias is shown in figure. p-n junction diode under forward bias. When an external voltage V is applied across a semiconductor diode such that the p side is connected to the positive terminal of the battery and the n side to the negative terminal, it is said to be forward biased. The applied voltage mostly drops across the depletion region and the voltage drop across the p side and n side of the junction is negligible. This is because the resistance of the depletion region, a region where there are no charges, is very high compared to the resistance of the n side and p side. The direction of the applied voltage V is opposite to the built-in potential V0. As a result, the depletion layer width decreases and the barrier height is reduced. The effective barrier height under forwarding bias is V0 minus V. If the applied voltage is small, the barrier potential will be reduced only slightly below the equilibrium value and the current will be small. If increase the applied voltage significantly, the barrier height will be reduced and the current increases. Due to the applied voltage, electrons from the n side cross the depletion region and reach the p side where they are minority carriers. Holes from the p side cross the junction and reach the n side where they are minority carriers. This process under forwarding bias is known as minority carrier injection. At the junction boundary on each side, the minority carrier concentration increases significantly compared to the locations far from the junction. Due to this concentration gradient, the injected electrons on the p side diffuse from the junction edge of the p side to the other end of the p side. The injected holes on the n side diffuse from the junction edge of the n side to the other end of the n side. This motion of charged carriers on either side gives rise to current. The total diode forward current is the sum of hole diffusion current and conventional current due to electron diffusion. The magnitude of this current is usually in milliampere. The circuit arrangement for studying the VI characteristics of a diode, that is the variation of current as a function of the applied voltage, is shown in figure. The battery is connected to the diode through a potentiometer or rheostat so that the applied voltage to the diode can be changed. For different values of voltages, the value of the current is noted. A graph between V and I is obtained as in figure. Forward bias measurement, we use a millimeter since the expected current is large. You can see in figure that in forward bias, the current first increases very slowly, almost negligibly, till the voltage across the diode crosses a certain value. After the characteristic voltage, the diode current increases significantly, that is exponentially, even for a very small increase in the diode bias voltage. This voltage is called the threshold voltage or cut-in voltage, is similar to 0.2 volt for a germanium diode and is similar to 0.7 volt for a silicon diode. The PN junction diode primarily allows the flow of current only in one direction. PN junction diode under reverse bias. When an external voltage V is applied across the diode such that the N side is positive and the P side is negative, it is said to be reverse biased. The applied voltage mostly drops across the depletion region. The direction of the applied voltage is the same as the direction of barrier potential. As a result, the barrier height increases and the depletion region widens due to the change in the electric field. The effective barrier height under reverse bias is V0 plus V. This supersedes the flow of electrons from N to P and holes from P to N. Thus, diffusion current decreases enormously compared to the diode under forwarding bias. The electric field direction of the junction is such that if electrons on the P side or holes on the N side in the random motion come close to the junction, they will be swept to its majority zone. This drift of carriers gives rise to current. The drift current is of the order of a few microampere. This is quite low because it is due to the motion of carriers from their minority side to their majority side across the junction. The drift current is also there under forwarding bias, but it is negligible, that is microampere, when compared with current due to injected carriers, which are usually in milliampere. The diode reverses current is not very much dependent on the applied voltage. Even a small voltage is sufficient to sweep the minority carriers from one side of the junction to the other side of the junction. The current is not limited by the magnitude of the applied voltage but is limited due to the concentration of the minority carrier on either side of the junction. The current under reverse bias is essentially voltage independent up to a critical reverse bias voltage known as breakdown voltage VBR. When V is equal to VBR, the diode reverse current increases sharply. Even a slight increase in the bias voltage causes a large change in the current. If the reverse current is not limited by an external circuit, below the rated value the PN junction will get destroyed. The circuit arrangement for studying the VI characteristic of a diode, that is, the variation of current as a function of the applied voltage, is shown in figure. The battery is connected to the diode through a potentiometer or rheostat, so that the applied voltage to the diode can be changed. For different values of voltages, the value of the current is noted. A graph between V and I is obtained as in figure. For the diode in reverse bias, the current is very small, that is similar to microampere, and almost remains constant with change in bias. It is called reverse saturation current. However, for special cases at very high reverse bias breakdown voltage, the current suddenly increases. The forward bias resistance is low as compared to the reverse bias resistance. This property is used for rectification of AC voltages. For diodes, we define a quantity called dynamic resistance as the ratio of a small change in voltage delta V to a small change in the current delta I. RD is equal to delta V upon delta I. Equation 6. Example 4. The VI characteristic of a silicon diode is shown in the figure. Calculate the resistance of the diode at A. ID is equal to 15 milliampere and B. VD is equal to minus 10 volt. Solution. Considering the diode characteristics as a straight line between I is equal to 10 milliampere to I is equal to 20 milliampere passing through the origin, we can calculate the resistance using Ohm's law. A. From the curve, at I is equal to 20 milliampere, V is equal to 0.8 volt. I is equal to 10 milliampere, V is equal to 0.7 volt. RFB is equal to delta V upon delta I is equal to 0.1 volt upon 10 milliampere is equal to 10 ohm. B. From the curve, at V is equal to minus 10 volt, I is equal to minus 1 microampere. RRB is equal to 10 volt upon 1 microampere is equal to 1.0 into 10 raised to 7 ohm. Application of junction diode as a rectifier. From the VI characteristic of a junction diode, we see that it allows current to pass only when it is forward biased. So, if an alternating voltage is applied across a diode, the current flows only in the part of the cycle when the diode is forward biased. This property is used to rectify alternating voltages, and the circuit used for this purpose is called a rectifier. Half-wave rectifier. If an alternating voltage is applied across a diode in series with a load, a pulsating voltage will appear across the load only during the half cycles of the AC input during which the diode is forward biased. Such a rectifier circuit, as shown in figure, is called a half-wave rectifier. The secondary transformer supplies the desired AC voltage across terminals A and B. When the voltage at A is positive, the diode is forward biased and is conducts. When A is negative, the diode is reverse biased and it does not conduct. The reverse saturation current of a diode is negligible. The reverse breakdown voltage of the diode must be sufficiently higher than the peak AC voltage at the secondary of the transformer to protect the diode from reverse breakdown. Therefore, in the positive half cycle of AC, there is a current through the load resistor RL and we get an output voltage as shown in figure, whereas there is no current in the negative half cycle. In the next positive half cycle, again we get the output voltage. Thus, the output voltage, though still varying, is restricted to only one direction and is said to be rectified. Since the rectified output of this circuit is only for half of the input AC wave, it is called a half-wave rectifier. Full-wave rectifier. The circuit using two diodes, shown in figure, gives output rectified voltage corresponding to both the positive as well as negative half of the AC cycle. Hence, it is known as a full wave rectifier. Here the P side of the two diodes is connected to the ends of the secondary transformer. The N side of the diodes are connected together and the output is taken between this common point of diodes and the midpoint of the secondary of the transformer. So for a full wave rectifier, the secondary of the transformer is provided with a center tapping, and so it is called a center tap transformer. As can be seen from figure, the voltage rectified by each diode is only half the total secondary voltage. Each diode rectifies only for half the cycle, but the two do so for alternate cycles. Thus, the output between their common terminals and the center tap of the transformer becomes a full wave rectifier output. Note that there is another circuit of full wave rectifier which does not need a center tap transformer but needs 4 diodes. Suppose the input voltage to A with respect to the center tap at any instant is positive. It is clear that at that instant the voltage at B being out of phase will be negative as shown in figure. So, diode D1 gets forward biased and conducts, while D2 being reversely biased is not conducting. Hence, during this positive half cycle, we get an output current and an output voltage across the load resistor RL as shown in figure. In the course of the AC cycle, when the voltage at A becomes negative with respect to center tap, the voltage at B would be positive. In this part of the cycle, diode D1 would not conduct but diode D2 would, giving an output current and output voltage across RL during the negative half cycle of the input AC. Thus, we get output voltage during both the positive as well as the negative half of the cycle. Obviously, this is a more efficient circuit for getting rectified voltage or current than the half wave rectifier. Filters. The rectified voltage is in the form of pulses of the shape of half sinusoids. Though it is unidirectional, it does not have a steady value. To get steady DC output from the pulsating voltage, normally a capacitor is connected across the output terminals parallel to the load RL. One can also use an inductor in series with RL for the same purpose. Since these additional circuits appear to filter out the AC ripple and give a pure DC voltage, so they are called filters. Role of capacitor in filtering. Now we shall discuss the role of capacitor in filtering. When the voltage across the capacitor is rising, it gets charged. If there is no external load, it remains charged to the peak voltage of the rectified output. When there is a load, it gets discharged through the load and the voltage across it begins to fall. In the next half cycle of rectified output, it again gets charged to the peak value. The rate of fall of the voltage across the capacitor depends inversely upon the product of capacitance C and the effective resistance RL used in the circuit and is called the time constant. To make the time constant, large value of C should be large. So capacitor input filters use large capacitors. The output voltage obtained by using a capacitor input filter is nearer to the peak voltage of the rectified voltage. This type of filter is most widely used in power supply. Special purpose PN junction diodes. We shall discuss some devices which are basically junction diodes but are developed for different applications. Zener diode. It is a special purpose semiconductor diode named after its inventor C. Zener. It is designed to operate under reverse bias in the breakdown region and used as a voltage regulator. The symbol for Zener diode is shown in figure. Principle: regulating supply voltages. Composition: Zener diode is fabricated by heavily doping both P and N sides of the junction. Due to this, depletion region formed is very thin, that is less than 10⁻⁻⁶ meter, and the electric field of the junction is extremely high, that is similar to 5 into 10⁶ volt per meter, even for a small reverse bias voltage of about 5 volt. The IV characteristic of a Zener diode is shown in figure. Working: when the applied reverse bias voltage V reaches the breakdown voltage Vz of the Zener diode, there is a large change in the current. After the breakdown voltage Vz, a large change in the current can be produced by almost insignificant change in the reverse bias voltage. In other words, Zener voltage remains constant even though current through the Zener diode varies over a wide range. This property of the Zener diode is used for regulating supply voltages so that they are constant. Let us understand how reverse current suddenly increases at the breakdown voltage. We know that reverse current is due to the flow of electrons, that is minority carriers, from P to N and holes from N to P. As the reverse bias voltage is increased, the electric field at the junction becomes significant. When the reverse bias voltage V is equal to Vz, then the electric field strength is high enough to pull valence electrons from the host atoms on the P side which are accelerated to N side. These electrons account for high current observed at the breakdown. The emission of electrons from the host atoms due to the high electric field is known as internal field emission or field ionization. The electric field required for field ionization is of the order of 10⁶ volt per meter. Zener diode as a voltage regulator. When the AC input voltage of a rectifier fluctuates, its rectified output also fluctuates. To get a constant DC voltage from the DC unregulated output of a rectifier, we use a Zener diode. The circuit diagram of a voltage regulator using a Zener diode is shown in figure. The unregulated DC voltage, that is filtered output of a rectifier, is connected to the Zener diode through a series resistance Rs such that the Zener diode is reverse biased. If the input voltage increases, the current through Rs and Zener diode also increases. This increases the voltage drop across Rs without any change in the voltage across the Zener diode. This is because in the breakdown region, Zener voltage remains constant even though the current through the Zener diode change. Similarly, if the input voltage decreases, the current through Rs and Zener diode also decreases. The voltage drop across Rs decreases without any change in the voltage across the Zener diode. Thus, any increase or decrease in the input voltage results in increase or decrease of the voltage drop across Rs without any change in the voltage across the Zener diode. Thus, the Zener diode acts as a voltage regulator. We have to select the Zener diode according to the required output voltage and accordingly the series resistance Rs. Example 5. In a Zener regulated power supply, a Zener diode with Vz is equal to 6.0 volt is used for regulation. The load current is to be 4.0 milliampere and the unregulated input is 10.0 volt. What should be the value of series resistor Rs? Solution. The value of Rs should be such that the current through the Zener diode is much larger than the load current. This is to have good load regulation. IL is equal to 4.0 milliampere. Choose Zener current as 5 times the load current. That is, Iz is equal to 20 milliampere. The total current through Rs is is equal to IL plus IZ is equal to 24 milliampere. The voltage drop across RS is equal to 10.0 minus 6.0 is equal to 4.0 volt. This gives RS is equal to 4.0 volt upon 24 into 10 raised to minus 3 ampere is equal to 167 ohm. The nearest value of the carbon resistor is 150 ohm. So, a series resistor of 150 ohm is appropriate. Slight variation in the value of the resistor does not matter. What is important is that the current IZ should be sufficiently larger than I. Optoelectronic junction devices. We have seen so far how a semiconductor diode behaves under applied electrical inputs. We learn about semiconductor diodes in which carriers are generated by photons, that is, photoexcitation. All these devices are called optoelectronic devices. Optoelectronic devices. Number 1, photodiodes, that is, photodetectors. Number 2, light emitting diodes, that is, LED. Number 3, photovoltaic devices, that is, solar cells. Number 1, photodiode. Principle which convert optical radiation into electric current. Composition. A photodiode is again a special purpose PN junction diode fabricated with a transparent window to allow light to fall on the diode. It is operated under reverse bias. Working. When the photodiode is illuminated with light, that is photons with energy HV greater than the energy gap Eg of the semiconductor, then electron-hole pairs are generated due to the absorption of photons. The diode is fabricated such that the generation of EH pairs takes place in or near the depletion region of the diode. Due to electric field of the junction, electrons and holes are separated before they recombine. The direction of the electric field is such that electrons reach N side and holes reach P side. Electrons are collected on N side and holes are collected on P side, giving rise to an electromotive force. When an external load is connected, current flows. The magnitude of the photocurrent depends on the intensity of incident light, that is, photocurrent is proportional to incident light intensity. It is easier to observe the change in the current with change in the light intensity if a reverse bias is applied. Application. Thus, photodiode can be used as a photodetector to detect optical signals. The circuit diagram used for the measurement of IV characteristics of a photodiode is shown in figure and a typical IV characteristics in figure. Example 6. The current in the forward bias is known to be more, that is, similar to milliampere, than the current in the reverse bias, that is, similar to microampere. What is the reason then? No operate the photodiodes in reverse bias. Solution. Consider the case of an N-type semiconductor. Majority carrier density N is considerably larger than the minority hole density P, that is, N is much greater than P. On illumination, let the excess electrons and holes generated be delta N and delta P respectively. N dash is equal to N plus delta N. P dash is equal to P plus delta P. Here N dash and P dash are the electron and hole concentrations at any particular illumination, and N and P are carriers concentrations when there is no illumination. Delta N is equal to delta P and N is much greater than P. Hence, the fractional change in the majority carriers, that is delta N upon N, would be much less than that in the minority carriers, that is delta P upon P. The fractional change due to the photo effects on the minority carrier dominated reverse bias current is more easily measurable than the fractional change in the forward bias current. Hence, photodiodes are preferably used in the reverse bias condition for measuring light intensity. Number 2. Light emitting diode. Principle. which convert electrical energy into light. Composition: it is a heavily doped PN junction which under forward bias emits spontaneous radiation. The diode is encapsulated with a transparent cover so that emitted light can come out. Working: when the diode is forward biased, electrons are sent from N to P, where they are minority carriers, and holes are sent from P to N, where they are minority carriers. At the junction boundary, the concentration of minority carriers increases compared to the equilibrium concentration, that is, when there is no bias. Thus, at the junction boundary on either side of the junction, excess minority carriers are there which recombine with majority carriers near the junction. On recombination, the energy is released in the form of photons. Photons with energy equal to or slightly less than the band gap are emitted. When the forward current of the diode is small, the intensity of light emitted is small. As the forward current increases, the intensity of light increases and reaches a maximum. Further, an increase in the forward current results in a decrease in light intensity. LEDs are based such that the light emitting efficiency is maximum. The VI characteristics of a LED is similar to that of a silicon junction diode, but the threshold voltages are much higher and slightly different for each color. The reverse breakdown voltages of LEDs are very low, typically around 5 volt. So care should be taken that high reverse voltages do not appear across them. LEDs that can emit red, yellow, orange, green and blue light are commercially available. The semiconductor used for fabrication of visible LEDs must at least have a band gap of 1.8 electron volt. Spectral range of visible light is from about 0.4 micrometer to 0.7 micrometer, that is from about 3 electron volt to 1.8 electron volt. The compound semiconductor gallium arsenide phosphide, that is gallium arsenide phosphide, that is gallium arsenide 1-X phosphide X, is used for making LEDs of different colors. Gallium arsenide 0.6, phosphide 0.4, that is Eg is similar to 1.9 electron volt, is used for red LED. Gallium arsenide, that is Eg is similar to 1.4 electron volt, is used for making infrared LED. Application: these LEDs find extensive use in remote controls, burglar alarm systems, optical communication, etc. Extensive research is being done for developing white LEDs which can replace incandescent lamps. LEDs advantages over conventional incandescent low power lamps. Number 1. Low operational voltage and less power. Number 2. Fast action and no warm-up time required. Number 3. The bandwidth of emitted light is 100 angstrom to 500 angstrom. It is nearly monochromatic. Number 4. Long life and ruggedness. Number 5. Fast on-off switching capability. Number 3. Solar cell principle which convert optical radiation into electricity. Composition: a solar cell is basically a PN junction which generates electromotive force when solar radiation falls on the PN junction. It works on the same principle, that is photovoltaic effect, as the photodiode, except that no external bias is applied and the junction area is kept much larger for solar radiation to be incident because we are interested in more power. A simple PN junction solar cell is shown in figure. A P-type silicon wafer of about 300 micrometer is taken over which a thin layer, that is similar to 0.3 micrometer, of N-type silicon is grown on one side by diffusion process. The other side of p-type silicon is coated with a metal, that is back contact. On the top of n-type silicon layer, metal finger electrode or metallic grid is deposited. This acts as a front contact. The metallic grid occupies only a very small fraction of the cell area, that is less than 15%, so that light can be incident on the cell from the top. Working. The generation of electromotive force by a solar cell when light falls on it is due to the following three basic processes: generation, separation and collection. Number 1. Generation of EH pairs due to light with HV is greater than EG, close to the junction. Number 2. Separation of electrons and holes due to electric field of the depletion region. Electrons are swept to N side and holes to P side. Number 3. The electrons reaching the N side are collected by the front contact and holes reaching P side are collected by the back contact. Thus, P side becomes positive and N side becomes negative, giving rise to photovoltage. When an external load is connected as shown in the figure, a photocurrent IL flows through the load. A typical IV characteristics of a solar cell is shown in the figure. The IV characteristics of solar cell is drawn in the fourth quadrant of the coordinate axis. This is because a solar cell does not draw current but supplies the same to the load. Semiconductors with band gap close to 1.5 electron volt are ideal materials for solar cell fabrication. Solar cells are made with semiconductors like silicon, that is Eg is equal to 1.1 electron volt, gallium arsenide, that is Eg is equal to 1.43 electron volt, cadmium, tellurium, that is Eg is equal to 1.45 electron volt, copper indium selenide, that is Eg is equal to 1.04 electron volt, etc. The criteria for the selection of a material for solar cell fabrication are: number 1. Band gap, that is 1.0 to 1.8 electron volt. Number 2. High optical absorption, that is similar to 10⁴ centimeter raised to -1. Number 3. Electrical conductivity. Number 4. Availability of the raw material. And number 5. Cost. Sunlight is not always required for a solar cell. Any light with photon energies greater than the band gap will do. Application: solar cells are used to power electronic devices in satellites and space vehicles and also as power supply to some calculators. Production of low-cost photovoltaic cells for large-scale solar energy is a topic for research. Example 7. Why are silicon and gallium arsenide are preferred materials for solar cells? Solution: the solar radiation spectrum received by us is shown in figure. The maxima is near 1.5 electron volt. For photo excitation, HV is greater than EG. Hence, semiconductor with band gap is similar to 1.5 electron volt or lower is likely to give better solar conversion efficiency. Silicon has Eg is similar to 1.5 electron volt, while for gallium arsenide it is similar to 1.53 electron volt. In fact, gallium arsenide is better in spite of its higher band gap because of its relatively higher absorption coefficient. If we choose materials like cadmium sulfide or cadmium selenide, that is Eg is similar to 2.4 electron volt, we can use only the high energy component of the solar energy for photo conversion and a significant part of energy will be of no use. The question arises, why we do not use material like lead sulfide, that is Eg is similar to 0.4 electron volt, which satisfy the condition HV is greater than Eg. For V maxima corresponding to the solar radiation spectra, if we do so, most of the solar radiation will be absorbed on the top layer of solar cell and will not reach in or near the depletion region. For effective electron-hole separation due to the junction field, we want to photogeneration to occur in the junction region only. Digital electronics and logic gates. In electronics circuits like amplifiers, oscillators, etc., the signal, that is current or voltage, has been in the form of continuous time-varying voltage or current. Such signals are called continuous or analog signals. A typical analog signal is shown in figure. Figure shows a pulse waveform in which only discrete values of voltages are possible. It is convenient to use binary numbers to represent such signals. A binary number has only two digits, 0, say 0 volt, and 1, say 5 volt. In digital electronics, we use only these two levels of voltage as shown in figure. Such signals are called digital signals. In digital circuits, only two values represented by 0 or 1 of the input and output voltage are permissible. Logic gates are used in calculators, digital watches, computers, robots, industrial control systems, and in telecommunications. A light switch in your house can be used as an example of a digital circuit. The light is either on or off depending on the switch position. When the light is on, the output value is 1. When the light is off, the output value is 0. The inputs are the position of the light switch. The switch is placed either in the on or off position to activate the light. Logic gates. A gate is a digital circuit that follows a certain logical relationship between the input and output voltages. Therefore, they are generally known as logic gates. Gates because they control the flow of information. The 5 common logic gates used are NOT, AND, OR, NAND, and NOR. Each logic gate is indicated by a symbol and its function is defined by a truth table that shows all the possible input logic level combinations with their respective output logic levels. Truth tables help understand the behavior of logic gates. These logic gates can be realized using semiconductor devices. Number 1. NOT gate. This is the most basic gate with one input and one output. It produces a one output if the input is 0 and vice versa. That is, it produces an inverted version of the input at its output. This is why it is also known as an inverter. The commonly used symbol together with the truth table for this gate is given in figure. Number 2. OR gate. An OR gate has two or more inputs with one output. The logic symbol and truth table are shown in figure. The output Y is 1 when either input A or input B or both are 1s. That is, if any of the input is high, the output is high. This gate can be used for modifying the pulse waveform as explained in the following example. Example 8. Justify the output waveform Y of the OR gate for the following inputs A and B given in figure. Solution. Note the following. At t is less than t1, A is equal to 0, B is equal to 0, hence Y is equal to 0. For t1 to t2, A is equal to 1, B is equal to 0, hence Y is equal to 1. For t2 to t3, A is equal to 1, B is equal to 1, hence Y is equal to 1. For t3 to t4, A is equal to 0, B is equal to 1, hence Y is equal to 1. For t4 to t5, A is equal to 0, B is equal to 0, hence Y is equal to 0. For t5 to t6, A is equal to 1, B is equal to 0, hence Y is equal to 1. For t is greater than t6, A is equal to 0, B is equal to 1, hence Y is equal to 1. Therefore, the waveform Y will be as shown in the figure. Number 3. AND gate. An AND gate has two or more inputs and one output. The output Y of AND gate is 1 only when input A and input B are both 1. The logic symbol and truth table for this gate are given in figure. Example 9. Take A and B input waveforms. Sketch the output waveform obtained from AND gate. Solution. For t is less than or equal to t1, A is equal to 0, B is equal to 0. Hence, Y is equal to 0. For t1 to t2, A is equal to 1, B is equal to 0. Hence, Y is equal to 0. For t2 to t3, A is equal to 1, B is equal to 1. Hence, Y is equal to 1. For t3 to t4, A is equal to 0, B is equal to 1. Hence, Y is equal to 0. For t4 to t5, A is equal to 0, B is equal to 0. Hence, Y is equal to 0. For t5 to t6, A is equal to 1, B is equal to 0. Hence, Y is equal to 0. For t is greater than t6, A is equal to 0, B is equal to 1. Hence, Y is equal to 0. Based on the above, the output waveform for AND gate can be drawn as given below. Number 4. NAND gate. This is an AND gate followed by a NOT gate. If inputs A and B are both 1, the output Y is not 1. The gate gets its name from this NOT AND behavior. The figure shows the symbol and truth table of the NAND gate. NAND gates are also called universal gates, since by using these gates, you can realize other basic gates like OR, AND NOT. Example 10. Sketch the output Y from a NAND gate having inputs A and B given below. Solution. For t is less than t1, A is equal to 1, B is equal to 1, hence Y is equal to 0. For t1 to t2, A is equal to 0, B is equal to 0, hence Y is equal to 1. For t2 to t3, A is equal to 0, B is equal to 1, hence Y is equal to 1. For t3 to t4, A is equal to 1, B is equal to 0, hence Y is equal to 1. For t4 to t5, A is equal to 1, B is equal to 1, hence Y is equal to 0. For t5 to t6, A is equal to 0, B is equal to 0, hence Y is equal to 1. For t is greater than t6, A is equal to 0, B is equal to 1, hence Y is equal to 1. Number 5. NOR gate. It has two or more inputs and one output. A NOT operation applied after the OR gate gives a NOT OR gate or simply NOR gate. Its output Y is 1 only when both inputs A and B are 0. That is, neither one input nor the other is 1. The symbol and truth table for the NOR gate is given in figure. NOR gates are considered universal gates because you can obtain all the gates like AND, OR and NOT by using only NOR gates.